everyone. It's been a little while since I've done a video, but I'm getting back into it. I've had quite a few bit of changes, and today's video is going to be on the Pythagorean Theorem. But it's going to be real brief. It's going to be a fairly basic introduction. Hey, I don't want yellow, I want purple. Purple's my favorite. So I'll put the updates of what's been going on with me in the comments, but real quick. I am not full-time teaching anymore. My leg injury from when I was in the military just got worse and worse, and to where I couldn't even stand in the classroom for more than 10 minutes. And so I'm doing part-time. And I don't know why I have this ruler out. Oh, I was playing with this smartboard. I have to use the basic version. A smartboard is the free version you can get. And I'm looking for another whiteboard type thing to use. But I haven't found anything as good as the smartboard as far as math tools and stuff like that goes. I'll keep a looking. I'm not that savvy with stuff. Alrighty, but being part-time, I get to do things like watch more shows like Panzer and Girls, one of the better animes out there. Also, I just like tanks. It's cool. Alright. Okay, so on to the Pythagorean Theorem. Well, everybody learns pretty early on, well before high school math, that the Pythagorean theorem is a squared plus b squared equals c squared. And that involves a right triangle, given that you have a leg, and a hypotenuse, okay? And these are the two legs. It doesn't matter which one you call A or B. And then you have C here. Normal naming convention, which is a convention. It's not actually a mathematical law. If you have the capital letter A here, opposite is going to be A. Capital letter B, opposite side will be B, little b. And capital letter C for that vertex will be little c over here. Okay? That's normal naming convention. But it's not a law. So what we have here is, I want to go through the history a little bit of Pythagorean because, you know, this is just kind of not as fun as the history and the proof and stuff, but it's a very important theorem. One of the most important theorems I actually do in high school because it leads up to a whole lot more, and we'll talk about that briefly again. Okay, it was known by the Babylonians and the Egyptians prior to Pythagoras, but what Pythagoras did was he played with it at a greater extent. So he was a pretty interesting person. He was born in, oh gosh, if I remember, here's the Greek world. All right, now this is approximately 500 BC. Okay, the Greeks were all over the place. They're colonizing, doing trade with the Phoenician, everybody. The future Carthaginians over here. Rome was just a tiny little village. The Etruscans going on, and Egyptians were in a little bit of disarray, but they're still there. Okay. So the Greeks were everywhere. This is before the time of Alexander the Great, which really expanded the Greek influence. And he was born in Samos, which is right here, but he primarily lived in Italy, southern Italy, somewhere around here. I'm not sure exactly where, but somewhere around there. Now, not far to the south of him, later on, like 500 years later, I think it was Punic Wars, Archimedes. He died during one of the Punic Wars. Lived in Syracuse down here. So some really great mathematicians lived in Italy, even though we call them Greek. Of course, some of the more famous Greek mathematicians lived in northern Africa, along Alexandria and some other place like Haran, Ptolemy, and so on. Okay, but really, really cool stuff that's going on with the Greeks. But the reason is this: is that even though the Babylonians over here and the Egyptians over here and a few other people here and there, make that go away, were dabbling in math, it was the Greeks that asked, why? Okay? This is huge. And when you get to geometry, you're going to learn your P's and Q's. And this is the heart of geometry right here, logic. And logic led to the scientific method, okay, so on. And that was by Apollonius. He lived over here somewhere as well. Apollonius, yes, and a few other very important people that developed that. Why is it this way? Because even though, come here, let's go to the next slide. Because even though the Babylonians used the a squared, well, they didn't actually use a squared plus b squared equals c squared, not in this form. This form was derived after Descartes. All right. This form was derived after we got to analytical geometry, which René Descartes basically started the whole algebra revolution, even though algebra was derived out of India and the Middle East to some extent. So what we have here is I've been big into circles. When I teach my advanced geometry class, I start off with circles. I really do. Day one, we're talking about circles, inscribed angle theorem, and so on. I ignore most of the books in Texas. So, Ptolemy's theorem, which you're not going to learn until after you learned, because a lot of high schools teach circles later on in the year, which is unfortunate because you need these proofs early in the year to prove some of the things that you do. So when you have this, you're going to have similar triangles, okay? And anybody who's already taken geometry has dealt with similar triangles and the inscribed angle theorem. And you get proportions where you have the chord theorem and things like that. We're just using that, basically Ptolemy's theorem, to prove this right here. And one of the more popular ways to write the Pythagorean theorem is c squared is equal to a squared plus b squared. And there's a lot of reasons for that, especially when you get into triangle inequalities and then the law of cosines. So this is what I tend to do after I get past that initial phase of geometry. I tend to write my Pythagorean theorem like this. Alrighty, so look this up on your own. Ptolemy's theorem proof. They got YouTube videos. I may do one in my future, but honestly, there's so many professional YouTubers out there that have really cool technology, and you know they're really smart in math. I'm just an amateur. Okay, so the Greeks, though, largely thought in natural numbers, and this is important. 1, 2, 3, 4, 5, 6, something like that. 0 was still being worked on. That'll be invented in India a little bit later. Okay, but you have 1, 2, 3, 4, 5, 6, and they used funny ways to write the numbers. So math, the way we think of it, is way different than the way they thought about it there. They did the area of this square plus the area of this square is equal to the area of this square. Because no matter how you did it, you're going to get a nice, easy number, as long as you're not dealing with strange, funky fractions or something like that. So say they had a 3, 4, and 5. They would have the area of this is 9. They wouldn't think of this as 3 squared. They think of this as 9. They would think of this as 16, and they think of this as 25. So they have 9 plus 16 is equal to 25. And the reason that's handy is because they'll have, let's just get a right triangle up here. There's one reason why I like this. Let's get a right triangle, okay? And the reason that the Greeks like this, because imagine having some 2, 3, and then x, all right? So you would have us, we would do 2 squared plus 3 squared is equal to x squared. But here, they're thinking, of course I drew terrible scores, 4 plus 9. So you would have 4 plus 9 is equal to 13. So that's how they would think of this in the terms of area. They would not think of this as the square root of 13. They would not think of c is equal to the square root of 13. They think of the area as 13. So they didn't have to deal with those pesky little radicals. Radicals were very, very hard to deal with. They knew they existed. They didn't understand them or how they fit in things. They would estimate them and say, well, you know, we're talking, you know, 3 point something, all right? And they didn't like it. In fact, they didn't like it so much that there's a rumor that Pythagoras drowned somebody because this situation came. Okay, let's take a square, and I show this in my geometry class on on how we derive the Pythagorean. So, or I mean, actually, when I do 45 special rights, I do this as well. So I have 1, 1, okay, and then we have our diagonal, which we could call D or C or whatever, okay? So we would have 1 squared plus 1 squared is equal to c squared, or the diagonal squared. So you'd have 1 plus 1 is equal to c squared, so c squared is equal to 2. C is equal to the square root of 2. Now this did not go, and this is something that the Pythagoras group was exploring. It was almost like a math cult. And he didn't like this. Everything had to be perfect, because in their minds, up to this point, when they started exploring this, They're looking at the square of 1 and 1. 1 plus 1 is going to be 2. So they're looking at the square of this, the area of the square of the hypotenuse is 2. Well, this caused problems. Pythagoras drowned somebody. That's legend. Okay, but he was also another kind of a nutcase. Well, I wouldn't call him nutcase. Maybe he was, probably, because he didn't like beans, or he avoided beans because they thought they were possessed by souls. And he would kill a poor ox every time they came up with something cool on mathematics. Okay. So how do we use this in basic geometry? We're going to do something different in later geometry. In your a lot of students take geometry in 8th or 9th grade, 10th grade, somewhere around there, depending on what school you're at or where you're at in your math studies. But we tend to use the analytical geometry aspect. So you have 2. And let's just call this one 3. Okay. And we already did this example. And we're going to look for c. So it's just going to be 2 squared plus 3 squared is equal to c squared. And if you wanted to, you could do it on a graph. Oh, where is my graph? I need a graph. Table, graph. Do I have graphs? Show math buttons, graphs. Okay, wait a second. I want to do a graph. Insert a Cartesian graph. I could do it like this. Okay, I could have I could have a 2. I can have a 3, and then I would have this. And oh, good grief! I am not used to this marker, so I'd have a right triangle here. Okay, so I could do it that way. Oh, good grief! I'll just do it this way. Come here, you. I would have something like this. Okay. So we can do it that way, but why bother? Because we know that the delta of this is going to be 2, this is going to be 3, and we want to know what this is. I can use the distance formula using 0, 3, and 2, 0, all right? And I can use the distance formula. The distance formula is derived from the Pythagorean Theorem. But why do that? I'm just going to do 2 squared, which is 4, plus 3 squared is 9, is equal to c squared. So c squared is equal to 13. C is equal to square root of 13. Now, in many geometry classes, mine included, we don't use a lot of calculators. We actually avoid them for most of the semester. We do a little bit when we hit trig and some of the harder math problems, application problems in the second semester. But we pretty much avoid it the first semester. So you would leave your answer like this, okay, and we'd simplify our radicals whenever possible. Okie dokie, moving on. So let's do 4, 6, and then we don't know what this is. So we're going to have 4 squared plus 6 squared is equal to, just call it c squared, all right? Because again, normal naming conventions, this will be little a, this will be little b, and this will be little c, opposites. You want to get used to that because that's going to pop up in later classes. And I would think almost 100% of all teachers use that convention worldwide. All right, so we have 16 plus 36 is equal to c squared. 36, 46 of 52, right? So c squared is equal to 52. The question is, can we break this down? All right, can any perfect square, 4, 9, 16, 25, 36, go into 52? Well, it looks like 4 can. It's going to be 4 times 13. So c squared is equal to 4 times 13. Take the square root on both sides. All right, so c is equal to 2 root 13. All right, and I have a separate video on simplifying radicals. All right. So what if we're not given, we're given something different, like here's a radical. And this is c, because it's opposite the hypotenuse. I could have called it some other letter if I wanted to. And here's our 2 legs. So we're going to do 6 squared plus x squared is equal to 6 radical 2 squared. Put that in parentheses. If you're not using a calculator, it shouldn't be a problem. If you're using a calculator, there's a high chance you're going to make a mistake because it's just going to square the radical 2 and not the 6. Put that in parentheses. So you have 36 plus x squared is equal to 36 times 2. So that's going to be 36 times 2, which is equal to 60 plus 12, 72. All right. So I'm going to subtract 36, gives me 36, and that's a perfect square. So x is equal to 6, the positive value of the root. So this is actually an isosceles right triangle. It has some special properties to it, but it's not drawn to scale. And very often, math teachers will not draw to scale just to throw you off, to make sure you're using the right definitions. Okay? So that's pretty much how you do it. Peek at the future. This is important. So this c squared is equal to a squared plus b squared. It's going to be a pretty big deal. You're going to learn about acute, obtuse, and right angles and how to determine that. And you're also going to learn something about the law of cosines, where you have c squared is equal to a squared plus b squared minus something. Okay? That something is going to be negative 2ab cosine c. Okay? And that's going to be a big player in, if you're taking advanced geometry, you'll see that in your geometry class. If not, you'll probably see it in your pre-cal class. All right? Okie dokie. So, without the Pythagorean Theorem, life would not be near as interesting, and they would never be able to build the space cruiser Yamato. Alrighty? So that is it for today. I hope you all have a good and fine and happy rest of the week. And I'll see some of y'all in class tomorrow, because tomorrow's a work day for me. Alrighty. See ya.